who's a grad student at UC San Diego, but here for the year. He's working with me and Mohan Paturi, and he'll talk on algorithms for unique games.
Okay, so let me start with sort of an overview of what I'll talk about. First, what is a unique game? And then, since the talk is on algorithms for unique games, what's the current state of the world as far as unique games algorithms? And then state and give the general idea of our results. And then give the details of the proofs. So, first point, what is a unique game? So unique game is you could think of it as a type of constraint satisfaction problem on a graph. So you have a graph, and you want to assign a label to each vertex, and the labels come from a set of size k, and we'll just think of them as being numbers 1 through k. It doesn't really matter what they are. Associated with each edge of the graph, so for an edge uv, we have a permutation associated with it. We'll call the permutation pi uv, and it's over the set of labels. And the goal is to come up with some labeling for the graph. So mapping from vertices to labels to satisfy as many edges as we can. And we say an edge uv is satisfied if the label for v equals the permutation on the edge of the label for u. For any labeling, we'll say the value of the labeling is the fraction of edges it satisfies. And then we'll say the value of the game overall is the value of the best labeling. So here we have a lot of symbols, but what does this actually mean? So a simple example of a unique game is max cut. Have a graph. And your set of labels you can think of as two things, left and right, or 1 and 2, whatever. And your permutations on each edge, it's the same permutation for every edge, and it just says that if this vertex is labeled 1, then this one should be labeled 2, and vice versa. So you go through, you label it, that gives you a cut, and the value of the cut is exactly what you would think of for max cut. Another example of a unique game is a system of linear equations in 2 variables over some finite group. So you'll have your variables x1 through xn, so like the vertices of your graph. And then you'll have some constraints, x1 minus x7 equals 3, say mod 20. So we're looking at 20 possible labels. x15 minus x4 equals 9, and so forth. But your unique game doesn't have to be anything nice like this. You can have whatever graph you want, and you can have some permutation that says 1 maps to 2, 2 maps to 1, 3 maps to 3, 4 maps to 47, so forth. It doesn't have to be anything nice like we've seen here. And just sort of as a sanity check, if you're looking at one of these things and the value of the game is 1, this is saying we can satisfy all the edges, then it's really quite trivial to find a satisfying assignment. The idea is you pick an arbitrary vertex and you pick a label for it. So we start here, we pick 1, that implies that this should be 2, this should be 2, this should be 2. Well, this game doesn't really have value 1 if it's max cut, but assuming it did, it just propagates out using, yeah. So if the value is 1, it's easy. But what if the value is close to 1? So in general, we'll be looking at unique games with value 1 minus epsilon for some small constant epsilon. And then as far as algorithms go, we'll try to figure out, given a unique game with this value, what fraction of the edges can we actually find a labeling to satisfy? But before I go into algorithms, let me just say a couple of quick words about why anyone actually cares about such things. So in 2002, Subhash Kote proposed the unique games conjecture. And this conjecture states that for all epsilon bigger than 0, so the idea is take epsilon as small as you want, there exists some set of labels depending only on epsilon, such that it's NP hard to distinguish value 1 minus epsilon from value epsilon. Thus far, it's not known whether the conjecture holds or not, but if the conjecture holds, then this implies at least a handful of new hardness of approximation results. And it also implies that semi-definite programming gives optimal approximations for a large class of constraint satisfaction problems. So if the conjecture holds, it's great. We get lots of.
What's the quantification of the graph? There exists the graph and there exists the labeling. There exists the game, so to say.
K epsilon is probably the size of the.
No, then there is a family, like for once you fix epsilon and k, the computational problem is an arbitrary worst case graph.
Oh, okay.
It's like, k sat or whatever. It's just a epsilon k unique game. And you could have other slight variants of this where this epsilon and this aren't the same and things like that. But essentially, this is the gist of it. So I'm not going to say too much more about why people care about them, other than just if the conjecture is true, we get lots of new results. And then I'll talk about algorithms. So looking at the current state of the world as far as unique games algorithms. So Charikar, Makarichev, and Makarichev gave an algorithm that every time, we'll assume we're starting with something with value 1 minus epsilon. Their algorithm gives a labeling of value 1 minus square root epsilon log k. And just to note, this is only really of interest if epsilon is less than 1 in log k. It also turns out that if you can do much better than this, as far as the relationship between epsilon and k, you end up refuting the unique games conjecture. And I think this is due to Coate, Kindler, Mossel, and O'Donnell. I don't remember the year. So we won't particularly look at the relationship between epsilon and k, since that's in some sense solved. Gupta and Talwar gave an algorithm that returns a labeling of value 1 minus epsilon log n. And again, this is only interesting when epsilon is less than 1 in log n. Trevisan gave an algorithm similar, order cube root epsilon log n. Same range of parameters where it gives something interesting. Aurora, Coate, Kola, Stier.
So Gupta and Talwar is an improvement of Trevisan.
Yes. I mean, they approach it completely differently, but it's an improvement as far as the result they get. But they both are effective in the same range of parameters. And Vishnoi give an algorithm that returns a labeling of roughly order 1 minus epsilon over lambda. And then lambda is the second smallest eigenvalue of the normalized Laplacian. In some sense, the bigger lambda is, the more it's an expander. So, and it's between 0 and 1. That's sort of all the properties you really need of it. And then our results, we give 1 minus order cube root epsilon over phi alpha squared log 1 in alpha squared, approximately. I'm leaving off log terms that aren't particularly relevant. And I'll get to what phi alpha and alpha are in just a second. 1 minus order cube root epsilon log 1 in alpha squared, and 1 minus c plus 1 epsilon. So in this case, this is interesting when epsilon is significantly less than lambda. Since I'm leaving off log terms, it has to be enough less. Here, when epsilon,
What's the second term? What's the second? 1 minus what? C plus 1 epsilon?
yes.
So you haven't said what the catch for the last two is yet.
Yes, there's a catch to both of these.
And you haven't said what is C. Okay, you haven't said.
Well, C you can think of as 2, but that's not the catch.
Also, there is no log factor anymore. This epsilon that went on to, it was removed by the Voghera checks.
Okay, well, even better. In ours, there are extra log factors that aren't particularly interesting, but are there. So here, epsilon has to be less than phi alpha over log 1 in alpha squared. This one runs in time 2 to the alpha n times some polynomial in n. And this last one runs in time 1 over 1 minus 1 in c to the n. So in this case, think, for example, if c is 2, it gives you a 1 minus 3 epsilon labeling in time 2 to the n. And this is a relatively simple algorithm, but we'll use it as a building block for this algorithm. And here, we require that epsilon is less than 1 in log 1 in alpha squared, or equivalently, alpha is at least 2 to the minus 1 in square root epsilon. So as epsilon goes to 0, alpha can go to 0 very quickly. So the algorithm it's exponential time, but for small epsilon, it's small exponential time.
Do you know the relation of the connection of the running time in the previous always?
All of everything from here up is polynomial time.
This O hides something. If you have exponential time, you can do it. So this O should somehow depend. Is there a
What-
dependence between the running time and this O?
Which O?
All of them, like.
So you ask, like, if there is a natural way to scale up the previous algorithms so that they perform better with more time?
Yes.
No.
Not obviously, no.
So, in fact, I think the running time for all the previous algorithms is identical. Or for maybe the Trevison's is or one of Trevison's is a counterexample, but
Basically, all of these are based on the same semi-definite program. Well, the Gupta and Talwar is a linear program, but in some sense, they're all dominated by however long it takes to run ellipsoid method or some such thing to solve the semi-definite program.
There is no way to embed a problem into a bigger problem, a natural way, so that.
Not obviously.
so like we were talking about like taking the graph and squaring it. But even that, you actually, every time you square the graph, since edges are now pairs of edges, you're actually doubling the epsilon. And since the crucial thing is to have epsilon as large as possible, or epsilon as small as possible, that's a lose in almost every situation, not just for running time, but for when the algorithms will work. So I don't know, there might be some clever way of doing it.
So the last algorithm, if you think of it as refuting the unique game thing, like the setting of 1 minus epsilon versus, I don't know, 110 for epsilon, then it's something like C would be set up to something like 1 over epsilon, which would have like running time of roughly 2 to the epsilon n.
Yeah. But, at some level, this last algorithm, its existence in life is because it's fairly straightforward and it's a building block for this one. So, while here you'll get 2 to the epsilon n, something like that. Here you get 2 to the alpha n, where alpha is exponentially smaller. So, here we can be quite content thinking of c to be 2, or 3, whatever, some small constant. And we don't really need anything more out of that last algorithm. So let me define now what phi alpha and alpha are. Well, here alpha is just a parameter that controls your running time. But it turns out it will play a similar role in this one. So let me explain what I mean by those there. So first, for any set of vertices, we'll say the volume of the set is just the fraction of degrees. So if the graph is regular, then the volume of a set is just the fraction of vertices in the set. And then we define the local conductance, phi alpha, as the minimum over all sets such that the volume of the set is at most alpha of the fraction of edges that leave the set over the volume of the set. So phi alpha will be between 0 and 1, and the bigger it is, in some sense, the more expansion, or more local expansion it has. And we can, in the special case of phi a half, this is just, in some sense, your normal notion of expansion, and we can use Jaeger bound to relate it to lambda from this. So it's kind of the general picture where we're working in. If you take this algorithm and choose alpha to be a half, then you can in some sense compare this algorithm to this algorithm because then the phi alpha, when alpha is a half, plays roughly the same role as lambda. And our result isn't as good as this, but it's in the same direction. However, if instead you choose alpha to be 1 in n, every connected graph has phi 1 in n of 1. You're just looking at all the edges that leave a vertex, and it's exactly the degree of the vertex. In which case we get cube root of epsilon log n squared. So in some ways you can compare this to these two in that case. So while at each end it's not quite as good as what was there previously, you get the sort of whole spectrum of algorithms by just varying your parameter alpha.
Is there a hope of making this phi alpha squared in losing the square then?
To lose this squared?
Yes.
We,
Always hope.
we haven't been able to do it, but we've been thinking about it. Yeah, because it would be nice to remove the squared.
Isn't that because of Chigurh's inequality or something with squares? Shouldn't it be there?
I mean, maybe you could do better than. I mean, that would be a
Cer-
slight improvement over AKKSTV. That's
Right.
But why shouldn't there be such an improvement?
Certainly, having it squared there by Chigurh's inequality, you're not saying anything new. But as you say, if
Or
you
alpha equals alpha.
for alpha equals a half, yeah. But if you can take off the squared, then this is better than this. But this.
So the square may be necessary using any kind of semi-definite program relaxation, which is what we're doing. So because there are the integrality gap examples, and I think they have relatively high expansion.
They
There's
have
some limitation that you get by looking at the.
they have enough expansion to be difficult, but not enough to be useful, in some sense. The integrality gap cases. So these two algorithms of ours are closely based on the AKKS-TV algorithm. We essentially change one part around and then build on top of what they did. So let me go over the general idea of what they did and then show how we change it.
Well, so before you do that, well, maybe you could give some examples of graphs with non-trivial phi alphas for alpha less than a half, but no real expansion.
Sure.
Or you doing
Well, yeah. Let me
It actually applies to a new class of graphs.
Let me put them here. So as sort of a trivial example, if you have two expanding graphs and then put them together with a small number of edges, it's now a horrible expander. But if you take alpha as, say, a quarter, it still has good phi alpha. And you can repeat this for a large number of reasonably good expanders with reasonably weak connections between them. So if you try to do this sort of thing, your lambda will be close to 0 because all of these are reasonably sparse cuts. However, they're sparse cuts where the two sides are both fairly big. So they don't really contribute to this. This is only looking where one side of the cut is sufficiently small. Okay.
No, but there is this, right? Or maybe that's useful just to understand the quantitative things. There are graphs with exactly these parameters, the integrality gaps things like perturb, the hypercube. That's exactly have this property, right? That they are bad expander for sets of size half, but as alpha shrinks, the expansion grows.
Yes.
But
It's still a bad example.
it's still a bad example even for your algorithms.
Yeah.
But maybe it's worth to do just to see the math why it's still.
I think you end up somewhere around this case. where alpha is roughly equal to 2 to the minus 1 in epsilon. So it's not, here we need alpha somewhat bigger than this. So if alpha is basically equal to 2 to the minus 1 in epsilon, it's not quite. I mean, your expansion is only, you don't have enough expansion on big enough regions.
So the basic thing is that you'd want to, you want psi alpha to be, so how does it work? You need alpha to be small enough so that psi alpha is what? Is like
Is you want alpha sufficiently small that psi alpha is like, or psi alpha, phi alpha squared is something like epsilon. Or you want this to be like, say, square root epsilon, or something along those lines. And you don't get it at the integrality gap case. So
Since you're also paying this log 1 over alpha, you have to get phi alpha large enough, comparable to epsilon, you need to make alpha exponentially small, then you won't get any.
yeah.
so maybe these integrality gaps actually maybe psi alpha already for half was, but maybe that's in max cut. Psi alpha already for half was something like epsilon, and then
Right.
and then it's just when alpha is very small, it actually tends to 1.
If alpha is sufficiently small in the integrality gap graph, you do get good psi alpha.
So alpha is basically 1, or like, I mean, like it's more than 2/3.
Yeah, if alpha is exponentially small in 1 in epsilon.
Yeah.
So
1 minus alpha to the epsilon, right? The epsilon per cube hypercube. But I guess maybe it's not the same epsilon. So anyway,
I think it is the same epsilon, or close, because I think they look at things with value 1 minus epsilon on the epsilon perturbed cube as they kind of the same.
and then expansion is like 1 minus alpha to the epsilon, right?
I think so, yeah. So if
But that means that you need to pick alpha.
so this means that epsilon log alpha should be, say, a constant.
It just means alpha 1 over epsilon is constant.
Yeah.
So if you take 1 minus phi alpha, and then take logs of that. No, so we need alpha to the epsilon to be bigger than a constant. Yeah, so epsilon log 1 over alpha has to be bigger than a constant. So then when you get an epsilon log 1 over alpha term,
Yes.
and you're
Yeah.
putting in your own notation.
So, in some sense, this points to the point where this kind of idea will end up breaking down. Because since this is based on SDP, even if it's getting close to the same trade-off point, you can't expect it to do better than the integrality gap.
Yeah, but I'm also a little confused actually. So I mean, if you look at the Weig-Schechmann graph or something, right? points at distance epsilon. Okay, so SP value is 1 minus epsilon, and phi for alpha equal to 4 is something like 0.99. Okay. As soon as you don't take, if you have any region on the sphere of measure much smaller than half the force would be good, then should have this expansion, should have good expansion.
Okay.
So they give 1 minus cube root of epsilon, right? Which is what.
Oh, okay. I mean, then the problem is that you give this cube root of epsilon thing,
Yeah.
so that's not a fun. So,
So if you, I mean, so
So
you
what-
don't expect it to be square root or something, right? So
yeah. So, what do we have to do to?
Why? Like it could be square root, right?
not better than square
Not
root.
better than
No,
square
Not
root.
better
You could
than-
have square root.
Yes.
So, but yeah, it should be said. I mean, phi alpha for some interesting graphs like the max gap instance, even for a fourth, it can be pretty big. But then the thing that prevents it from being interesting is this cube root.
So
to get rid of this cube root, I think you need phi alpha. When that this is become. Yeah, you don't get rid of this cube root at all. So
yeah.
this is only interesting for large k. And then for large k, the gap instances look a little different.
For
Yes.
large k, the gap instances don't have this property.
Right. So for large k, it's for small k, the gap instances have the property that for alpha even a fourth, they have good expansion. For large k, that's not true. You get a different. But I don't see how this k factors into this 1 minus alpha over epsilon. I think this is assuming that epsilon is something like 1 over log k. And then you get this phi alpha equal to 1 minus alpha.
As far as the algorithms go, it doesn't matter what k is. As far as what the graph has to look like,
Right, we're talking about the graph.
yeah. Then k is like,
Yeah, exactly. So the gap instances have expansion 1 minus alpha to the 1 over log k roughly. So
Yeah. okay. So let me now talk about what the AKKSTV algorithm does, and then how we'll change it. So at a very high level, the AKKSTV algorithm runs a standard semi-definite program, and this gives some notion of distance between pairs of vertices. And this distance is defined in such a way that the distance along an edge is very short. And then they combine the short distance on edges with expansion to get that if you take an arbitrary pair of vertices, on average, this distance notion will be small. And then they show that if you have this property where if you take any arbitrary pair of vertices, they have relatively small distance between them, you can then get a good labeling. And this small distance on average between arbitrary pairs of vertices is something like the average distance on edges divided by lambda. So here, the short distance on edges, edges will have length something like epsilon, and then average pairs of vertices will have length something like epsilon over lambda. And then you get the labeling of value, epsilon over lambda. So
What does it mean, small distance on average? That every pair.
Most of
take a random pair
of
and-
vertices, they
and
are
look at the
small.
expected distance. And it'll be something like this. So, as far as what we do, we'll keep this the same as AKKS TV. We'll keep this the same, and we'll change this part so that it no longer requires expansion, but in some sense it just requires a good phi alpha.
But you still keep the same that small distance on average at the end?
We'll change this slightly also. So it
So maybe you say why it's not true if you just have local expansion. Give some picture.
Maybe that dumbbell graph, like. which
yeah,
is-
exactly. You can have something weakly connected like that, and you could
Then definitely, you don't have to satisfy that constraint at all, so it could be completely arbitrary to completely
right.
arbitrary different.
suppose that you're assigning a number between 0 and 1 to each vertex of the graph. And then the distance between a pair of vertices, whether it's an edge or not, is just the difference in label. Then you can label this whole expanding graph with 0, this whole expanding graph with 1. The average distance along an edge is essentially 0. You have one edge of length 1, but now you take an average pair of vertices, and your different distance will be something like a half. So we'll change this a little bit and change this. Let's see. So in their proof, they show this based on the eigenvalue lambda. Let me instead show a combinatorial way you can argue essentially the same result in the case of a expanding graph. So we'll continue thinking about this case where each vertex of the graph is labeled with some number between 0 and 1. And we'll choose some threshold t uniformly between 0 and 1. Then we'll say that their set X is all the vertices whose label is less than t. So we'll say xv is the label on vertex v. So v such that xv is less than t. Set.
I'm sorry, what is XP? You're assuming you have a one-dimensional embedding of the vertices.
Right. So maybe you should spell out we have some graph G.
So we could think of it as this graph or some other graph like this. So
For every v, you have xv lambda equals 0.
and we'll think of this in some ways as a label for v. Not in the same sense as labeling a unique game, but just to give some notion of distance. And then we can define a metric delta on the vertices, where delta uv is exactly the probability that u and v are cut by x. And this is exactly xu minus xv, whether it's an edge or not. Now, we'll continue thinking about a case, for example, like this, but in general, a case where the average distance along edges is small. So the expected value of delta uv over edges is, say, epsilon. And now we want to look at the expected value on arbitrary pairs of vertices, u and v, whether they're an edge or, one is here and one is here, of delta uv. And we'll call this delta. Now, when we do this, when we choose this random set x, what's the expected number of edges that we cut? So the expected value of this is epsilon m. Each edge is cut with probability proportional to its distance, and we just average over all of them. Now, what's the expected size of the smaller half of the cut? Well, let's look at a random pair of vertices. What's the probability that they're cut? So let's say that Cx is the fraction of pairs of vertices that are cut. And the expected value of Cx is delta. Now, say Fx is the fraction of vertices on the smaller side. So this is just now we have that Cx is exactly 2 times Fx times 1 minus Fx. So if you pick a random pair of vertices, it's cut if the first one you pick is in the smaller side, and the second one you pick is in the bigger side, or if the first one you pick is in the bigger side and the second one you pick is in the smaller side, hence the 2. And we can just crudely bound this by 2 Fx.
I think you want the other, greater than or equal to. Sorry, wait. Okay.
This
It's less than or equal. Sorry, you're right.
is less than 1, less than or equal to 1. Okay. Now, essentially, we just put all the pieces together. So for any x, the number of edges from x to that cross the cut is at least phi a half times, here I'm just going to pretend that x is the smaller size of the cut just to write less, times the number of edges. Now, let's see. The expected value of this is epsilon m. So this is and here we're really just looking at the smaller side, not necessarily x. But the expected value of the, or the expected size of the smaller side of the cut is the expected value of fx times the number of vertices. Or oh, right.
You forgot this phi a half times the size of x.
It should be the volume of this.
Yeah, it should be the volume of x. So that essentially gets rid of this. Or, right.
Everything is normalized.
Let's assume that it's a regular graph for now.
Okay. In which case, if it's all normalized, then we don't have an m here. So we're looking at, let's normalize everything. So the fraction of edges cut is at least phi x times the volume of x. And this is,
Expectation of what you called f.
yeah, and then this is,
Which is larger than 10,000.
which is,
Times by
yeah, phi a half. So this gives us that delta is less than 2 epsilon over phi a half. So if the average distance along edges is short, epsilon here, it's an expander, or it has good conductance, then delta has to be small, where delta is the average distance on pairs of vertices.
You have to lose a square somewhere, right?
In this case, no, because we're assuming we can label them in this way.
You lost it then, so that's where you lost it.
Yes, essentially.
Or we're doing things in terms of phi rather than lambda.
Well,
If you bound phi, the only relationship between phi and lambda would be phi is at least lambda squared.
No, but I thought you're not improving a KSTV.
we're not. We're just thinking about it differently.
So, okay, so
Because this could be more easily generalized to phi less than a half than looking at the eigenvectors and eigenvalues. This does assume that we define this distance in terms of some sort of label that we put on the vertices such that we can choose this distribution on cuts. It's essential that we have some distribution on cuts and then define delta as the probability that a pair of vertices is cut. So we need this, and we need this small, and this at least some constant, ideally. So what we will end up with is, here let's see, I guess I erased it, but here we say if the average distance on edges is close, the average distance on arbitrary pairs of vertices is close. But we see from this example that as soon as alpha is less than a half, that can't be true. So what we'll ask is, instead of being able to say that the average distance on arbitrary pairs of vertices is small, we'll ask that we can partition the graph into sets such that the average distance within a set is small. So, the average distance here is now 0, the average distance here is now 0, and we'll also ask that we only cut a small number of edges between sets. And we do, we cut one edge here.
Where does this argument break down? Taking phi halves, right? Like you would not be able to write that statement with phi alpha.
You can't write this with phi alpha, and it's because,
The splitting is about half.
yeah, I mean, here we're looking at two cases where we're just saying that fx is the smaller side.
But if it was phi third,
So it doesn't rule out a half of partition, right? With very few cuts.
So the key point is we're looking at the minimum of the volume of X and the volume of X complement.
That should be at
oh,
most.
right.
One of them
okay.
is at most a half.
Okay.
Right. And, when alpha is less than a half, it breaks down completely.
For this reason, the graph might even be disconnected.
Yeah.
So what you just said, if indeed the graph is disconnected, then you sort of have two different problems, and you
That's
solve
right.
on each one separately.
That's right. And so what we're trying to argue, the whole point which we're trying to argue is that's the general case.
But if you have a few edges, you cut along these edges to two different problems, and this is a good
Right.
idea.
And this
Yes.
distance will tell us not only, the distance that we have will also tell us where to cut. So
Right.
just given the graph, it's probably very hard to find a good cut. But once we have this distance, that tells us where to cut.
You still didn't tell us how you get this distance. So that's,
I will. I'll get there.
I think what Boaz asked is still not clear to me. Why is this not an improvement over EKKSTV? Because they cannot replace
You
the
can't-
lambda by phi half.
You can't do this.
Okay.
I mean,
No, but I think it's, so what you should say, go back up to the top.
yeah,
So
phi half is larger
phi
than
half
lambda,
is
so it's
lambda.
better than lambda. So it
Yeah.
would have been an improvement if you could do this and really retain the same epsilon.
yes, if you could maintain epsilon and
Get to just one number rather
Oh,
than
here
vector.
Do that.
you would lose when you say the average distance is epsilon.
yeah, you either don't get that the average distance is epsilon, or you can't label things with a single number in this way. So we show how we can get around this, and then we show what happens in the general case. And then taking things one step further, when we get to our weakly exponential time algorithm, we say, okay, well, if we don't have any phi alpha, what happens when we run this algorithm anyway? Here, essentially the idea was, if there's too many vertices on the small side of the cut, that implies there have to be many edges cut. However, we know we're cutting only a small number of edges. Therefore, the small side of the cut has to be small. So if we don't have this, and it's the same intuition when we go to the alpha less than a half case. But if we no longer have any conductance, and we try to apply the same argument, we get that we'll get some set of cuts. We'll partition the graph into some sets, and these sets will fall into one of two categories. The sets will either be very small, they'll be less than alpha volume of vertices, or they'll have roughly the same value. And then it follows fairly directly from that we can get the sort of weakly exponential time result, because on the sets that have roughly the same value, we can use the same idea as AKKS-TV. And on the sets that are very small, at most alpha n, we'll use this algorithm with, say, C as 2. But let me actually go through the details of what happens and what we do.
So your 2 to the alpha time, 2 to the alpha n is just because you're doing an exponential search over sets of size alpha.
Yes,
The other parts are good anyways.
yes. And it's essentially the same sort of partitioning that gives us these small sets. So let me go into somewhat more detail about what the algorithm actually does. So we start with essentially the same semi-definite program as AKKS-TV, which is to maximize the average over all edges UV of the average over all labels I of UI V pi UV of I. And here UI, you can think of this as saying U should get label I, and 0 if U does not get label I. And what value it actually gets when U does get label I, it will be some big vector. And we can think of it as these two vectors are sort of the same when when U gets label I and V gets label pi I. So they're the same and they're big when the edge is satisfied.
I guess it's up to normalization, but you want this expectation over I, so the vectors are not unique vectors, they're like magnitude k when they are.
Yes, they're magnitude.
That means the sum over.
It's expectation. When you have one big vector, it's like,
It's the same, I mean, it's
Yeah.
a choice. I just want to make sure that I understand the choice.
yeah. No, I've done everything in terms of expectation. You can scale sort of the whole semi-definite program by a factor of 1 in k if you want. So if U gets label I, you can think of it as having value root k 0. And if it doesn't get label I, you can think of it as having value all 0. And then whatever this, if the game has value 1 minus epsilon, and you label it according to this rules, then this objective function gives you exactly the value of the game. And then the constraints are for all U.
Yeah, I'm not sure if maybe it's good. I mean, we need to just write expectation with like E and slightly different font than the same E for the edges.
Oh,
Yeah.
make these bold. There. Okay. So this we can think of as saying U gets one label. Actually, yes, these two together give us that U we think of as getting one label. Really, it just means that they're If it has multiple labels, they're orthogonal. And then this, our algorithm doesn't particularly use. We just include it because it's needed for a lemma of AKKSTV that we use. And then finally, triangle inequality. In this L2 squared space of semi-definite program constraints.
So you need this triangle.
What?
Does your algorithm need this triangle?
Need it? Strictly no. It just simplifies things a little bit and it doesn't hurt, so we throw it in.
You need a strong version where the triangle equals are across vertices. Sometimes you just see with for all u and for all I think. So
We do need it between vertices for how we use it. You know, you can get a slightly weaker version, change a constant somewhere without it, but it keeps things simple. And it doesn't hurt the semi-definite program at all. So then again,
Did they use it?
AKKSTV didn't, no. They define a distance rho uv as the minimum over all permutations sigma of and this is essentially just the Earth mover distance, but we look at whatever permutation sigma minimizes this, and that defines this distance. And then we say sigma uv is the minimizing permutation of this same thing. We have that the average rho uv over edges is at most epsilon. And the idea for this is if we take this quantity and combine this with this fact, we get this quantity is equal to 1 minus ui v sigma I. And if instead of sigma here, you plug in the actual constraint on the edge, the average of this quantity would be exactly epsilon, assuming the semi-definite program has value 1 minus epsilon. And taking the minimum overall permutations only makes it better. So, thus far this is all from AKKSTV, except for the slight detail of the triangle inequality, which doesn't change things. Let's see. So now our algorithm will run our partitioning. And for now, I'll just state what we get, and then I'll finish the algorithm. And then later on, I'll go through the details of the partitioning. So we partition V into sets S1 through S2 to the L, where L is some constant, such that for at least a 1 minus R volume of vertices V, the probability of a random, you take a random vertex U in V's set. So we'll say by SV, it's whichever of these sets V happens to be in. The probability rho U V is bigger than R is less than R. And R will end up being something like this. And an R fraction of edges are cut. So we get back these sets such that, and this is in the polynomial time case where we have some constant local conductance. And R here is something like cube root epsilon over V squared. And there's other log terms, but they're of less importance. Given that, what we'll do is we'll go through set by set and label it. So for each set, we want to make sure that we don't choose any vertex as sort of the center of the set that's in the R volume of vertices that our partitioning doesn't say anything about. So we'll think of those in some sense as being outliers, that maybe are vertices in the wrong set, or in some sense we can't say anything too much about them. However, since rho is something we can easily compute, when we're looking at a vertex, we can easily test to see if it's one of the R volume of outliers or not, and if it is, we'll just try something else. So we'll choose, as I said, some vertex to be the center, and we'll label U with label I with probability proportional to its semi-definite programming vector. And then, actually, let's call this V and this V. Or I'm bound to mix things up when I write things wrong from my notes. Now, for each U in SI, we'll label it with sigma VU of I. So this gives us a labeling for the whole set. Now, it's possible that we have some set such that everything is an outlier in some sense, but then the size of the set is small and we just throw it away. You know, it's at most, there's at most a total volume R of such sets, so it doesn't really hurt us to throw them away. So this is essentially from AKKS-TV. And it's fairly straightforward, so I'll actually show what happens. So to figure out how likely this is to actually satisfy an edge, we have V. We have some edge UW, and we think of all of these as being in SI. And here we have some distance rho UV, and here we have some distance rho VW. And here we have some distance in slightly a different sense that I'll call epsilon UW. And what epsilon UW is exactly this, but with pi instead of sigma. So the actual constraint on the edge. So the average over all edges of epsilon is exactly the epsilon of the completeness of the game. Now, what's the probability that the edge here is not satisfied by this labeling? Well, I claim that that's exactly the probability that we choose an I for label V such that the compositions of the permutations around the triangle doesn't equal I. So we'll say, just call pi the composition of sigma UV and then pi UW and then sigma VW. So the probability that UW is not satisfied is where I'm saying that this one sub I doesn't equal pi I, just an indicator of this happening. So here essentially we're just summing up the probability that we've chosen a bad I. But this equals so for each I, we'll just include the other label. And obviously it can't match up either. So we get these are equal. Now, this follows from all the various VIs being orthogonal. And I guess this.
You want an inequality.
Right. Now here we can just use our triangle inequality to look at the distance around the triangle. So this is at most a half the expectation I VI, so we'll go clockwise around it, minus U yeah. Pi W U U V. And then plus the same thing for the third leg of the triangle. But this is just exactly rho VU plus epsilon UW plus rho WV. So now for an average edge in SI with probability 1 minus R, these both are less than R. This is on average epsilon. So on average, we end up satisfying this edge with probability something like 1 minus order R.
Another order R edges that we're not even trying.
Right, yeah, well there's order R edges that get cut. We can, if we have sets that are all outliers, we'll just ignore all of them. But each thing contributes at most to order R, and we just sum them up. And there's a small number of cases to consider, and we end up with order R. So assuming we can do the partitioning as I claimed, we end up with this algorithm. And thus far it's basically just following a KKS-TV. Let's see. In the case where we don't have any local conductance, we'll try to still do the same partitioning. So now we'll look at this algorithm and same semi-definite program, get the same distances, slightly different partitioning. So what we'll get here is we partition it into the same sets such that we cut at most R fraction of edges. And thus far, it's the same. But here for a 1 minus R volume of vertices V, we have either that the volume of V's set is at most alpha, or the same probability bound. And since this is something we can check, we can quite easily figure out which case we're in and so forth. For each set falling into this category, we'll do the same thing.
And what about this edges cut?
Cut at most an R fraction of edges. And here R,
Cut at most. You cut at most R fraction of edges. That's generally true. Okay.
yeah, regardless of which case here, we always cut at most an R fraction of edges. And then this is sort of looking one set at a time. It's either at small or
Why do you need, if it's small, why even bother? I mean, I don't know what is 1 over minus 1 over c algorithm, but why not just completely brute force it, do it in time 2 to the...
So the reason is that you can't do it in time 2. So exhaustive search is time k to the n.
And you didn't want k to the n.
Yeah.
Okay. But you can enumerate over all the constraints that you guess are wrong and
But that would be 2 to the m.
2 to the m. Okay.
the C plus 1 epsilon is close to what we do. It's a slightly clever brute force search. And that's, yeah, exactly what we do. These ones we solve like we did before. These ones we solve using the bottom algorithm, and that gives us this result, again, assuming we can partition and get this R. So now let me talk about what this algorithm does, and then I'll talk about how we partition things.
This can reduce to constant degree or
But the constant depends on k.
on epsilon.
On k.
Okay.
Because the number, at least a priori, it seems to, because there are k to the n possible colorings in the unit of approximation for each one. So then you can reduce it to like 3 log k.
So here we'll start by assuming the existence of some good labeling for the graph. And then each edge of the graph, we'll say it's good if it's satisfied by L and it's bad otherwise. And now what we'll give is a randomized algorithm that succeeds with probability 1 minus 1 in C to the n. And what we'll do is we'll construct a forest in G. So as long as there are at least C epsilon fraction of edges between trees in F, we add a random edge.
In between trees.
Yeah, we add a random edge between trees.
That's the total number of edges between
Right. And then when we finish, we have our spanning tree. Yeah, spanning forest, not necessarily a tree.
It spans almost all of the.
It spans most. There's a small fraction of edges that go between the trees in our forest. For each tree in the forest, we label it with the optimal consistent labeling, where the entire tree is satisfied. And that's easy to do. And then we just output the best labeling. We do each tree independently, output the best overall labeling. Now, what's the probability that we fail? Well, we fail anytime we ever add subsets a bad edge to one of our trees. Where a bad edge is something that's not satisfied by L. And that happens with exactly this probability, or well, at most this probability, this part. And we add fewer than n edges at most to our forest. So this is the total probability of failure. And then as far as the value of the solution, well, there's C epsilon fraction of edges that we just completely throw away. They're the ones going between different trees in our forest. And there's an epsilon fraction of edges that are violated by L. These are our edges. If we have some tree, they're edges like this, between parts of the same tree that just don't get satisfied anyway, even by an optimal labeling.
So just a second. So finally, you output the best labeling for each forest. Tree.
For each tree, yes. Yeah, so we throw away the C epsilon edges between trees.
Can't we say or argue that there are not too many dependent trees, and then you could say if there are at most even log n, or say at most a constant number of trees, then you could even find the best between the trees, and then you wouldn't lose a C there. You just get say something like 2 epsilon or 3 epsilon.
I see. So we could make, if there weren't too many components, we could make a graph, where each node was one labeling of the component, or was one represented a whole component. We're still fixing everything in the tree to be true.
Yes.
And then really brute force it. Just try everything.
If you have small number of components, you
Well,
can
so
use
it's still a unique game, except it's sort of a weighted.
It's a
unique
weighted game, yeah.
Uh,
For our particular case, choosing C equals 2 and, we get 1 minus 3 epsilon is plenty good. So, once we got something that was good enough and independent of K, we stopped thinking about it. So, you're quite right. It potentially could be improved. So now all that remains.
Is this about similar to what Luca did? Because this is like the other extreme of the algorithm.
I don't think it's similar to what he did.
I don't know, I'm just asking. Because
The only combinatorial, non-semi-definite program algorithm. So he had two algorithms. One was SDP based, and one was based on random walks. So, but even with the random walk case, then he was getting a log n factor because the average, the distance between nodes is log n.
Yeah, here essentially we accept that we're going to take a huge amount of time, but we end up getting a good labeling.
when you started, you said that your algorithm interprets
Oh, that,
Well, just in terms of the performance, but
Yes, I
not,
understand. And on one hand, you used the idea of one algorithm, the ideas of, so I thought that maybe it really interpolates between the ideas, but I was wrong.
the log n in Luca's algorithm comes from decomposing the graph until every part is an expander.
so, yeah, and, but also from the diameter of the expander, so even if it started as an expander, you'd get a log n.
I think so, yeah. I don't remember the details of his semi-definite
We
program
actually
one.
had a previous paper that was never published that did interpolate Luca's idea, looking at shorter random walks.
Generally, in an expander,
But,
you
it depended on, the time depended on K.
generally, I guess that's a way to. I mean, if you walk like in an expander, as long as your walk doesn't get you start from a vertex and you just take a walk, then you'll get something like epsilon times the diameter.
Yeah.
Because, that's the probability you're not hitting a bad edge. So
Yes. And that's what his was based on.
That plus decomposing into expanders and then running that on each component.
there is something. I mean, you also try to walk and not hit a bad edge.
I guess in some sense it's somewhat similar to that, but here we make very sure we don't hit it. We don't accept the sort of epsilon log n fraction of bad edges.
By basically, looking at the low probability event that you don't.
Yeah.
You might say that you're running Luca's algorithm, but you're crossing your fingers and hoping to be really, really lucky.
But we're not, but we're not picking the edges along the path. We're picking the edges sort of all throughout the graph.
If you do a random walk and stop it when you hit something, you
Well,
construct a tree like this.
Yeah.
This gives you a uniform distribution on spanning trees.
So,
So it's,
This doesn't, though, right? If you just
so you stop it before you conclude.
but even if you
It's similar. I'm not.
yeah, but even if you continue this till you have a tree, don't you end up with a different distribution on trees?
Some distributions.
Anyways, we're running out of time. Should I talk about how we actually partition things? How long does this go for?
Have 15 minutes.
Okay. Let me at least try to give the idea of how we partition things. So let's start by thinking, in this case, where we want to cut a small fraction of edges, and then for each set, we'll let it either be small or have a similar value. So this will be our first goal. Also, for the sake of simplicity, let's think in the case where we can, for example, assign a number between 0 and 1 to each vertex and then cut things the same way. But in general, let's just say we have some distribution on cuts, along the same lines of what we did before. And so and then we'll say that delta uv is exactly the probability that u and v are cut. And we'll use delta as our notion of distance for now. And assuming there's enough time, I'll explain how to connect it to the real distance rho that we care about. So we'll start by assuming we have two parameters, delta and L. And delta, for now, eventually we'll pick them to be whatever optimizes, a couple of equations. But it'll end up that delta is something like square root epsilon log 1 in alpha. This is also where we're saying epsilon is the average delta along an edge. And L is something like square root 1 in epsilon, log 1 in alpha. And there'll be other log terms and whatnot, but that's roughly the idea. L is just another parameter. It'll be an
But it's the
integer
same
with
L
about,
as above.
yeah, it's the same L as above there. Yeah. So what we do is we independently choose x1 through xl from our distribution D. So, we have our graph, and if it's if it has local conductance, it may look something like this, and then we have a bunch of edges and whatnot. But then we choose this set of cuts in the graph. So, one cut may be here, one may be here, one may be here, something like that. Now, each of these will become one of the sets. It doesn't really matter how we order them, just each set is sort of the region and the intersection of all these cuts and the opposite sides of the cuts. And now we'll just argue that essentially doing this has roughly the properties we want.
So you're going to hazard their intersections in the HTTP solution?
Basically, yeah. So for any pair U and V, the probability that they're in the same set is exactly 1 minus delta UV to the L. Just the probability that they're not cut L times. Then, for each vertex, we'll define the set of vertices that are far from it while still being in the same set as everything that's in its same set but that's at least delta away from it. So for example, if we pick this vertex as V, then f of V may be all of this. Now the expected volume of vertices that are far from V is the probability that a random vertex is far from V. Which is, well, at most this. Because to be far from V, delta UV has to be at least big delta, and it has to be in the same set. Let's see. We'll define a set W, and this will be all the outliers. So a vertex is an outlier if it has many vertices that are far from it. And what we pick here as our definition of far from it, or lots of things far from it, is just what's needed to make the math work nicely later on. Now, the expected volume of outliers is exactly the probability that some vertex is an outlier. And the probability that some vertex is an outlier is the probability that this is bigger than this. However, we have a bound here on the expectation of this, so we just use Markov's inequality to get that this probability is at most
Everything cancels except the delta over 3.
right. I suppose that's better than writing everything and then canceling it. Yeah, so that's why we chose this anyway. And then the probability that the volume of our outliers is bigger than delta is at most a third. So from this, we get that there's a small number of outliers. Now, we'll look at vertices that are not outliers and that are in a big set. So we want something along these lines. So the probability that we pick some u in V's set that's far from it is the fraction of things that are far from it over the fraction of things that we can choose from. Yeah. Well.
F of V is the thing inside. F of V is the things that are far and inside the set.
Yes. Yes. And then this is at most.
So you bind it by just the things that are far from it.
Because if it's not in W, then this is we can upper bound. And if it's big, we can lower bound this and we combine them. Now, we choose delta and L in such a way that this is at most delta. And this, you could think of this as one of our equations that we're solving when we actually solve to optimize the parameters. But for now, I'll just claim that that's what we get. The next thing is we want to argue that few edges are cut. So each edge is cut with probability at most delta, delta of the endpoints of the edge. So the expected fraction of cut edges each time is epsilon, and we cut L times, so we cut at most epsilon L edges. And then again, by another Markov's inequality, the probability that we cut more than 3 epsilon L is a third. So with probability at least a third, both this happens and this happens. And then the other equation that we want to essentially solve for is this. And you find delta and L to satisfy those. You end up somewhere around here with more log terms and more messiness. And that gives you the partitioning in the case of allowing small sets. Now, in the case where you have some good conductance, phi alpha, instead of insisting that the number of edges cut is at most delta, we'll insist that it's at most phi alpha delta. Again, you just find the right values for delta and L, satisfying that constraint. And then look at the sets that the partitioning outputs. Now, for each set, we'll say it's small if its volume is at most alpha. So the sum overall small sets Si of the edges leaving Si is it, well, it's at least phi alpha number of edges, the sum of their volumes, right? And it's at most the total number of cut edges. Times 2, right, because each one can be counted twice. And then there's a...
How did you write sum of the volumes of SI?
No, he just, the number of edges cut, he chose the equation so that it's at most
Just SLs are small.
Yeah, if they're small, they have to have many edges leaving them, just by the definition of phi alpha. And then from this, we can cancel this, and then we get that 2 delta upper bound,
Small set is
the total volume of small sets. And again, these are all summing over all the small sets. So this part is similar to what we did 2 hours ago.
So instead of solving them using a brute force algorithm,
we ignore them.
we ignore them.
And then in 1 minute, I will quickly say what we do to get the distribution on cuts from the SDP
But that's also
vectors.
largely just taken from.
It's 90% taken from AKKSTV. So they give in their paper an embedding that produces vectors V for each vertex in the graph. They produce these big vectors such that this is at most rho is at most the same quantity like this plus for whatever constant t you want. So we take these vectors and we just cut them with a random hyperplane to give a distribution on cuts on vertices.
I should say that they're also individually they're norm 1.
Yeah, each of these is a unit vector. They're in some high-ish dimensional space, but it doesn't really matter.
Then you just do hyperplane rounding.
We just cut them based on the hyperplane. That puts them in, that gives us our sets X. We do all this. And from this, because these are, it's the square of these distances that are close to rho, we get that delta UV is approximately square root rho UV. So it's this part that gives us many of the squares and whatnot in the results that keep things from being as nice as one might hope for.
Actually, better than this, I think squares is a hard problem. Is there a chance to prove the cube root? Do you see where instead of the cube root, a square root would be? I think is more plausible. I'm not sure I see where.
So part of the cube root comes from, we end up changing what we actually ask for so that, let's see.
So if we did it like you spelled out up there, it would be really fourth root rather than cube root, right?
Right.
So we have one square root from that approximation and then one square root from the trade-off between that now.
We change things a little bit so that instead of asking that this probability that we're bigger than delta is at most delta, we change this to a delta squared. And then when we do that, when you combine this and this, you end up with the cube root. And again, this part, you just solve the math again for the slightly changed parameters, and that's what we get. So I'll just finish with a couple of thoughts on open problems. And one is, as various people have said, can you, by some method, improve this sort of result to get the square root to a cube root to a square root or get rid of it completely? You get this sort of trade-off where alpha has to be bigger than something like 2 to the minus 1 in square root epsilon. Can you do significantly better than this? And this is for something that runs in time 2 to the alpha n by any means. And then lastly, if the unique games conjecture holds, there has to be some class of graphs that are hard. Well, they're not expanders. They don't have good local conductance. And at the same time, they can't be too simple. They can't be a planar graph. So what sort of structure can they have so that they're actually hard? And that's all I have.